Just let me check whether the recording is started or not. Yes, it is started. So today our topic will be time response analysis. Okay, and this is one of the most important aspects of a system engineer or control system engineer, whatever you say, because normally we use time as an independent variable, and therefore it is of interest to evaluate the output or the state of the response of a system with respect to time. That is simply termed as time response. Because whenever you're studying or analyzing some system, you're actually interested in how the system behavior changes with respect to time. Okay. So what is time response analysis then? Generally, in the analysis process, a reference signal is applied and the performance of the system is evaluated by studying the system response in time domain. That is, the performance of the system is quantified or qualified as good, bad, satisfactory based on the response characteristics with respect to time. That is, analysis in time domain. Now, this time response can be divided into two clear or distinct parts. What are these two parts? If you remember, one part is your transient response, another part is your steady state response. So I think I have already in some previous lectures I have mentioned this transient and steady state responses. Can anyone recapitulate? What do you mean by a transient response and what do you mean by a steady state response? Can anyone tell me?
The transient response means temporary response, and steady state means permanent response. Transient response occur when the transient response occurs when we have switching action in the circuit or sudden change in the circuit.
Okay, right. ঠিক আছে. Good. I have an idea. Anybody else? Anybody else?
So ওটাই মানে এটাকে মানে চেঞ্জ ইন ইকুইলিব্রিয়াম স্টেটে মানে ইকুইলিব্রিয়াম থেকে যদি শিফট করে যায় তখনই তো ট্রানজিয়েন্ট থাকে।
Okay, another information, right? ঠিক আছে, very good. আর কেউ দুরকম পেলাম, ঠিক আছে।
টি ইকুয়াল টু ডেল টি মানে খুব কম সময় যে রেসপন্সটা ওটাকে স্যার ট্রানজিয়েন্ট বলতে পারে, স্টেডি স্টেট হচ্ছে এট টি ইকুয়ালস টু ইনফিনিটি।
না, এম ভাবে বললে হবে না, তোমাকে টি ইকুয়াল টু ডেল্টা টি বললে হবে না। তোমাকে যেমন জয়দ বললো, তোমার স্বরূপ বললো, স্বরূপ না কি নাম তোমার? শরফ,
শাহরুখ।
আচ্ছা, শাহরুখ বললো যে দুটো জিনিস ইম্পর্টেন্ট। এক নম্বর, তোমাকে একটা কোনো এক্সাইটেশন দিতে হবে, ঠিক আছে, কিংবা সিস্টেমে কোনো চেঞ্জ আসতে হবে। সিস্টেমে যে চেঞ্জ আসবে, হোয়াট উইল হ্যাপেন, দ্য সিস্টেম উইল মুভ ফ্রম এন ইনিশিয়াল স্টেট টু এ ফাইনাল স্টেট, কিংবা জয়তের কথা, ফ্রম ওয়ান ইকুইলিব্রিয়াম স্টেট টু অ্যানাদার ইকুইলিব্রিয়াম স্টেট ফলোইং দ্যাট এক্সাইটেশন or change in system condition. Now this transition from one state to another state, this transition occurs when this transition occurs, or the response during this transition is the transient response. Okay, it is that portion of the response. Then what is the steady state response? Once it reaches the new steady state value or the new equilibrium point, then it prevails, it stays there. If you do not give any excitation or the plant conditions are intact, then it will supposed to remain in that position even if we increase t, or ideally theoretically as t tends to infinity. That is why it is called a steady state response. And transient means it is moving from one steady state to another steady state. In between it is showing some transient, right? So steady state response is nothing but that portion of the response that remains after the transient portion has died out. That is, a movement from one steady state to another steady state has died out. Right? Suppose you are moving from your home to classroom, which is obviously a far off thing as if now, but your home is a steady state condition for you. You do some particular jobs when you're at home. The transient is how you come to your classroom. You may have a bus, you may have a train, metro, taxi, cycle, by walk. So there are different transients by which you reach, and each day how you reach your classroom may not be same, depending upon the dynamics of the traffic and things like that. But once you reach your classroom, your activities are again defined. So that is another steady state. But this transition from home to your classroom is a transient period. Once you reach the classroom, we assume that you are at a steady state because you are within, in terms of your location, you are within a particular point. Your activities will never reach a steady state. I can assure that. I have seen that. So you students are always in a transient mode. There is no settling down to any value or any point. But still, from location point of view, that's a steady state, right? So transient is your transition or the transport part. Similarly, in case of system theory, whenever you give an excitation, then you expect the system to move from one state to another state via a transient response. Now, a very, very important thing is that with reference to steady state response, some of you have a notion that a system is at steady state. That means its output should be steady. Exactly not. If the input is a ramp type of input, then output may grow like this. If the input is a sinusoidal input, then it will be moving in a sinusoidal manner. But what happens? The nature of the response becomes steady. We can express the response by using a simple mathematical expression. Transient response can also be mentioned or represented using simple mathematical expression. That's fine. But it will follow a particular pattern or a fixed pattern, right? Such that a sine wave or ramp function depending upon the input applied. So a steady state response never means a fixed response or a fixed value. It may have a variable value, but you should only say it has reached a steady state if the corresponding input is also changing. If you give a step response and if it's showing a sinusoidal, then it is not reaching the steady state. But if you give a sinusoidal and it is showing a sinusoidal, then you say, okay, it has reached the steady state. So depending upon the steady state response, characteristics of the behavior will depend upon the nature of the input. So with respect to the input, we have to state whether the steady state has reached or not. Understood? Now, next question is why this transient is exhibited? Why any system, any dynamic system exhibit this transient response? Why cannot it move from one steady state to another steady state instantaneously? Any idea?
Sir, because when there is a sudden change in the circuit, like switching action, sudden apply voltage, or sudden current applied.
Then what happens?
Then a transient occur.
Why? Why transient?
Sir, because of the presence of inductors and capacitors.
Right. In case of electrical circuits, inductor, capacitor, because they are very lenient. They are not very lenient to change. They always tend to oppose any changes, right? So it's like
Yes, sir.
inertia in a mechanical system. If there is inertia in a mechanical system, so you cannot move the mechanical system, or mechanical system cannot move instantaneously. Inertia, mass, things like this, right? So these are nothing but equivalent to electrical capacitor, inductor, as we've already seen in analogous systems, right? Mechanical to electrical analogous systems. So this very property of a system that dominates or that dictates this transient response. How the system will respond when given an excitation, right? This inertia, mass, or capacitance, inductance, depending upon these values, the transient response of a system will change, right? So from the transient response and steady state response, what we can conclude or what conclusion we can draw? First of all, from steady state response, given a particular input, we study the steady state response of the system, and following that, we can state whether the particular system reaches a particular steady state or not. Say you have given a step response, but the output response is continuously growing like a ramp function. So you say it is not reaching a steady state value. So it's an unstable system. per se. So given a ramp signal, if it moves like a ramp signal, then we say it has reached a steady state because it is now following the input signal, right? So by this way, we can state whether a system is actually achieving a steady state or not. For that, you need information on input signal and the output signal. Okay. From transient response characteristics, what you can do, you can quantify or you can qualify the system in different classes. I think you've already heard these things like underdamped, overdamped, critically damped,
Yes,
undamped,
sir.
right? So these are the different classifications that we apply to systems with different types of transient response. So the main portion or the main incentive of this response analysis is to characterize the system in terms of its transient response and to comment on the system stability, whether the system is stable or not. So to carry out this transient or the steady state analysis, what we need is an input signal. But very unfortunately, unlike some electrical systems and in communication systems, the input signal to a particular system in general are not fixed. They are random in nature. In electrical systems, we know whether we apply a DC voltage or an AC voltage, we know the nature of the system. In communication, there's a fixed frequency, carrier frequency, we know. But in other situations, you cannot specifically say what will be the input a particular system would be subjected to. So for that, we need to develop a basis on which we can analyze a system, because for time response analysis, we need an input signal. Say, for example, a radar. A radar is tracking a particular motion of a, say, missile or some target. But the motion of the target is completely random. You do not know where it will move from a particular point. So the input to the radar or the radar signal that will be generated will be completely random. You cannot say. Again, if you are moving with a aeroplane, when an aeroplane is moving, flying, it is never assured whether it will reach a air pocket, when a wind gust will come. These are exogenous inputs, or somehow it is called the disturbances. Right? So these things are never, you cannot predetermine this thing, or you cannot ascertain these things a priori. So what we have to do, we have to develop a methodology by which we can analyze the system in general. So what is the methodology? We should first define some standard test signal. Okay. So what is the concept behind it? Suppose a system is susceptible to a variety of inputs. You do not know what will be the nature of the input. There is no proper mathematical expression available to express that random input. So what you can do, you can classify the different types of input that will adversely affect or severely affect the performance of the system. Then we can assign certain inputs to these categories and find out the response of the system with respect to these individual categories. Now, since we're only dealing with linear time invariant or LTI system, because of this linearity property and the time invariance property, what you can say, if you know the performance of a system with respect to a particular signal or a set of signals, then the response with respect to any combination of these signals will be simply superposition of the respective responses, like superposition theory, right? Because all the responses are additive and it follows the principle of homogeneity and multiplicity. So this principle is used to obtain the time response for any signal by defining some standard test signals. To define the standard test signal, what we have to define first is the signals that severely strains a physical system. What are these? This can be classified as, say, number one, a sudden shock, right? Number two, a sudden change. with respect to input, right? These are all types of inputs. Number 3, a constant velocity. Number 4, a constant acceleration. So these are the 4 different situations that severely strains a physical system. Now we have to assign a particular signal with respect to these situations. A sudden shock that can be represented by, can you assign any particular signal, input signal? I think you've heard
Sir,
about
impulse.
Exactly.
Right.
Impulse, a sudden change.
Step.
Unit.
Step.
Right. A constant
Ram.
velocity.
Ram.
Right. An acceleration.
Parabolic.
Right. So these are the standard 4 standard signals that will be used to study the time response. Another signal that I have intentionally left alone is what is called, sorry, a sinusoidal signal. Okay, because this sinusoidal signal doesn't give any additional information regarding the transient and steady state response of a system. It can be very easily obtained from the previous 4 or any of the previous 4 responses. But this sinusoidal response is preserved for what is called frequency response analysis. These are all time response analysis. That is, we are arriving at output with respect to time. In sinusoidal signal, we will preserve for frequency response analysis. I'll just briefly tell you what happens. For a given LTI system, we apply a sinusoidal signal of a given amplitude and frequency. Then, keeping the amplitude fixed, we change the frequency of the sinusoidal input signal. Since it's an LTI system, the output at a steady state will also be sinusoidal, and it will have the same frequency at the input frequency. But with changing frequency, the amplitude of the output signal and the phase of the output signal with respect to the input signal will vary. So what is the procedure? With variable frequency over a wide range, we calculate the amplitude of the output signal and the phase of the output signal with respect to the input signal and plot them as gain versus frequency and phase versus frequency. They're normally plotted in log magnitude semi-log curve, and that gives you the frequency response data. And that is being used in board plot. I think board plot you have seen, BOD in filter design.
No, sir.
Shown here, na?
হ্যাঁ স্যার মানে শুনেছি কিন্তু জানি না।
Okay.
স্যার এমনি ডিএসটি স্যার বলেছেন যে মানে সিস্টেম পড়ানোর সময় আর কি পড়া হবে ওটা জাস্ট
এক্স্যাক্টলি আমার পড়ানোর কথা ডিএসটি স্যার আমাকেও বলেছেন তোমাদের পড়িয়ে দিতে, আমি পড়িয়ে দেবো। টাইম রেসপন্সটা হলে তাহলে ফ্রিকোয়েন্সি রেসপন্সটা পড়িয়ে দেবো, ঠিক আছে?
ঠিক আছে।
সো জাস্ট বলে রাখুন, না একটা সিগন্যাল আমি এখানে ইনকর্পোরেট করছি না, কোথায় সিগন্যালটা লাগবে সেটা বলে দিলাম। ওকে, সাইনুসয়েডাল সিগন্যালটা ফ্রিকোয়েন্সি রেসপন্স এখানে লাগছে। সো নেক্সট লেট আস সি ইন্ডিভিজুয়াল। তোমরা র‍্যাম্প, ইম্পালস, স্টেপ এগুলো সব জানো তো? আই গেস
ইয়েস স্যার।
তাও একটুখানি আমি রিলেট করে দিই, যে কোনটা কোথায় ইম্পর্টেন্স আছে একটুখানি বলে দিই। স্টেপ ইনপুট মানে it represents an instantaneous change in the input value. Okay, so an example, suppose input is an angular position is your input. So a step change in angular position means there is a sudden rotation in a mechanical shaft, right? So this is normally represented as RT is equal to AUT. It is the unit step function, right? And the definition is UT equal to 1 for all t greater than equal to 0 for all t less than 0, And obviously this RS is equal to A by S. This is trivial. So my question is, what information do you think a step input response will give you, will provide you? Any idea? What information do you expect from a step input response? Suppose it is at a 0-degree angle. Now you suddenly give an angular rotation of the input of 20 degree. Then what will happen? The output will also change. Now this will give you an indication about the system's quickness in responding to inputs when the inputs are changed abruptly. That is, the quickness in responding to abrupt changes in input. How quickly it can react. So it is giving you the quickness of response. How quickly it can react. I'm not drawing these responses, right? This is a very trivial thing. So ramp signal. Given your input is in angular position, so what does this ramp input will mean? It will mean that the angular position is continuously growing, because in this case, for step signal, what you have done, that you have given a particular value and say theta, and you have kept it at there. But in a ramp signal, what you have done, so it was at 0, then you have given a particular value, and it is keeping on increasing. It is continuously increasing. So what does that mean? If angular position, if this theta is angular position, the ramp input will be nothing but a
ওমেগা মানে মানে অ্যাঙ্গুলার ভেলোসিটি কি বললেন?
right, constant speed rotation.
Yes.
Right, and normally it is depicted as RT is equal to AT. I'll be using this step function to ensure that the input is only present after or from t equal to 0, right? That's why this UT will be added to all the signals. So corresponding RS will be simply A by SSC. Right? So it will give you an idea about how it can follow a constant change, right? Quickness is given in the step input. The ramp input will give you information how it can follow a constant change in input, right? Third one, I'm not following any order. It's a parabolic input. Now what does it mean? That means it's a constant acceleration, right? With respect to angular acceleration. As the velocity is not constant, it is also increasing. So normally, although it is very difficult to understand, okay, so I'll just leave with the expression, and your RS A by ST. Right? So last and not the least will be the impulse input, right? There is a sudden shock. Okay, so do you know what is an impulse input?
Delta T.
What is delta T? What is it called?
Dirac delta.
Dirac delta.
Right, right, right. So it is defined as a signal
Yes, sir.
which has 0 value everywhere except for at
T equals
t
to
equal
0.
to 0.
0.
Okay, and theoretically at t equal to 0, its magnitude will be infinity, right? এই অর্ণব আসতে চাইছিলাম, অ্যাড করে দিয়েছি, ঠিক আছে? Right? So normally it is defined as direct delta function, right? So it is defined as delta t equal to 0 for all t not equal to 0, and just mention this: epsilon tends to 0 minus epsilon to epsilon delta t dt is equal to 1, because a perfect impulse cannot be realized or cannot be achieved in practice. So what is done, we normally consider a pulse like this, right? If this is a, this thickness will be 1 by a. So we call this normally an unit impulse, because the area is unit under this. So this is normally defined. You can also define this delta t as your first derivative of step function. Follow? If you take a derivative of the step function, what you get? You'll get a spike, and that is your impulse response. And the further definition is that the Laplace transform of this impulse response is 1. So this property is very important. Why? I'll come to the next page. Okay, I'm coming over to the next page. This property is very important because suppose the impulse response of a system ys will be the transfer function into rs corresponding to impulse response. What is rs? Rs equal to 1. So it becomes simply gs. If you take inverse Laplace, then yt is equal to gt. So in time domain, the impulse response is called the waiting function of the system. You may ask that we already know that we can solve for the response in Laplace domain, and then finally you can take the inverse Laplace. But there may be some situations where you cannot apply this Laplace or inverse Laplace. Then what you have to do to find out the response for any given input, we can use this waiting function, like in this convolution integration. Right? This is a waiting function. So if you do not have the Laplace transform of input, or the input is not Laplace transformable, or the signal system is not Laplace transformable, but you know this waiting function gt, then you can apply this convolution integration theorem to obtain the expression for yt. So in these situations, this impulse response function or the waiting function is very, very important. And obviously, the transfer function of a system can be defined as the Laplace of this waiting function, right?
স্যার এখানে ইন্টিগ্রেশনের লিমিটটা মাইনাস ইনফিনিটি থেকে প্লাস ইনফিনিটি হলো না কেন?
কত ঠিকই বলেছো, কিন্তু আমি দেখো ফার্স্ট অফ অল আমি ধরেছি যে ইনপুট ইজ অনলি প্রেজেন্ট ফর t greater than equal to 0,
আচ্ছা আচ্ছা,
and secondly আমি at instant t তে ধরছি, সেটা t অবধি ইন্টিগ্রেট করলেই হবে।
হ্যাঁ হ্যাঁ,
এইটা কিন্তু সবসময় ওই জন্য আমরা প্রত্যেকটা ইনপুটের আগে একটা করে ut মাল্টিপ্লাই করে দিচ্ছি। ut মাল্টিপ্লাই করা মানে কি t less than 0 তে ডিফাইন্ড না 0, তাই না?
হ্যাঁ ঠিক আছে, হ্যাঁ
ওই জন্য ut টা করে দিচ্ছি, কারণ আমরা যখনই সিস্টেম অ্যানালিসিস করব কিংবা রেসপন্স অ্যানালিসিস করব, আমরা t equal to 0 থেকে শুরু করব। ওকে, তার আগে আমাদের যাওয়ার দরকারই নেই, তাহলে কি হচ্ছে, নট ইন্টারেস্টেড। So let us see the time response of first order system. Let us consider a first order system. Now, thing is that this is okay, trivial. This is a first order system. But if I want to represent this first order system, then I can represent this first order system in this manner. This is called a block diagram representation that will come right after this module or the time response module. Mind it, this is plus and this is minus. If you have this kind of representation in GS, which is nothing but defined as CS by RS, will come up like this. Now, why I am drawing this? Just to show you a particular phenomenon that is actually happening. I think you might be confused at how this 1 by TS plus 1 is coming, right? So let me briefly show that. Suppose you have a signal ES here. So what is your ES? RS minus CS. What is your CS? 1 by TS into S, right? Now just replace this any one of them over here. So what you can do is replace this. So 1 by TS. ES is represented as RS minus CS. So what you'll get, CS into 1 plus this portion, right, is equal to RS by TS. So following that, your CS and RS will be, their TS will get cancelled out. Followed? So this is your transfer function. How to calculate the transfer function for this particular block diagram. I'll discuss about the block diagram later. So just to take a note of this thing, that how this transfer function can be calculated. Now, if you want to obtain the response, your CS will be GS into RS with GS being 1 plus TS. Now say we're interested in step response, first of all. So it will be simply RS will be equal to 1 by S, unit step response, right? I should write unit step. So now the CS can be represented by partial fraction, and it can be represented as CS is equal to 1 by S minus 1 by S plus after partial fraction expansion. So for that, from that, what will be a CT? 1 minus e to the power minus T by capital T for T greater than equal to 0. So this is your expression for the time response of this first order system. If you want to draw this, and this portion is not visible. So first of all, what will be the steady state value?
One.
Yes. So this is the steady state value. I'm just drawing the steady state value. These are the response. So this is the steady state value. So how would the response look like? There will be, sorry. right? Exponentially varying, right? See, if you look closely, the value of the slope at this time t equal to 0 will be the maximum, and as t tends to infinity, the slope will become 0. Okay, so let me just move on to the next page and draw this figure clearly. Axis. Say this is the steady state value. This is a steady state value of 1, and the response will be something like this, right? So it will reach the steady state value 1. This is your CT, and this axis your time. Now, one important property is that, you know, when it reaches 0.632 or 63.2% of its final steady state value, that time is called the time constant of the system, and it can be found out from the expression. What is the expression? Ct equal to 1 minus e to the power minus t by capital T. So from that expression, this capital T is called the time constant of the system, right? This is the, I think this is known. Time constant of the system. So what are the conclusions? First of all, at t equal to 0. Okay. Now, initially, Ct at t equal to 0 is 0. But what about the slope? That is what about the slope? বলো কত হবে স্লোপটা?
1/t.
By again at t tends to infinity, Ct as t tends to infinity is 1. And what about the slope?
0.
So what happens? The value of Ct moves from 0 to 1, but the rate of change of Ct, which is maximum at t equal to 0, given by 1/t, continues to reduce, and it becomes actually equal to 0 when the steady state value is reached. Once it reaches the steady state value, the slope actually becomes 0. It splats out. So this is how the transient portion of a first order system can be defined. Now my question is, why this slope is continuously getting reduced, finally reaching the 0 value? Can you put any insight into this? কেন এটা হচ্ছে? Okay, I'll give an example. Then I guess you'll be able to understand this. It's very important. The transient কেন আসছে এটা বোঝার জন্য it's very important. The capacitor, right? When the switch was open, and if you consider this to be your output, when the switch was open, the capacitor stage is initially completely discharged. So the value of the output V0, what will be the value? It will be 0. Now, as soon as you turn on the switch at say t equal to 0, the switch is turned on. So what will happen? This entire E voltage will be applied across the capacitor. So the resistance obviously suddenly. So this will be like in step input, right? Now what will happen? This step input will cause a current to flow in this path. So this current, what it will cause? This current is basically dq dt. So it will cause some charge to accumulate in the capacitor. So as soon as some charge is accumulated in the capacitor, what will happen to VCT? It will be greater than 0, right? Now, when the capacitor was discharged at the instant, say at t equal to 0 plus, what will be I? That is I 0 plus is equal to E minus 0, since the capacitor voltage is not there, by R. And that is nothing but your, rate of charge accumulation, dq dt at t equal to 0 plus. That will be very high. But as soon as this capacitor voltage increases, what will happen? This expression for current, say t equal to 1 or t equal to more than 1, this expression of current will be changing. E minus Vc by R. দেখতে পাচ্ছ তো এটা? In general, the expression for current will now become IT will be equal to E is a fixed voltage minus VCT by R. But what is happening? This capacitor voltage is continuously increasing. So what will happen? The current will fall because of this difference voltage. So this difference voltage VC, which is the output voltage, will actually tend to oppose the flow of current. This is a property. And that will cause the rate of charge accumulation to get reduced because the current is getting reduced. So the rate at which the voltage was building up will get reduced. So this will continue until a steady state is reached. What is a steady state? When VCT is equal to E. That is, the capacitor is charged to the full potential of the battery source. Then what will be the value of current? Right? So obviously, under such conditions, there will be no more charge accumulation taking place. So the capacitor voltage will remain constant. Right? This is how this phenomena can be explained. And that is why I have drawn this figure. If this is the capacitor voltage, that particular voltage will come over here. So if I redraw this figure, how it will look like? If I redraw the figure, it will look like something like this. Say this is your ES plus, and this is your VCS, because block diagram is normally drawn in Laplace domain, minus. So this differential voltage, when multiplied by 1 by R, what will give? Your IS. This IS, when multiplied by 1 by CS, it will give you VCS. This will be feedback. So if you multiply these two, so your 1 by TS is equivalent to 1 by RCS. So T is nothing but your RC. That follows the time constant. So this is how this basic block diagram is formed. This is called a block diagram. এটা আমি পরে পড়াবো ডিটেইলস এ। এখন মনে হলো এটা সিম্পল এক্সাম্পল যখন করাচ্ছি, এটা দিয়ে দেওয়াটা খুব দরকার। তাহলে এই ফর্মুলাটা বুঝতে পারলে কি হচ্ছে, বেসিক্যালি capacitor voltage grow করছে, it is tending to oppose the flow of current or rate of charge accumulation. That is why the growth rate is getting reduced, right? So this is how the step response of a system will look like. So if you write down the, sorry, I should not write step response. unit step response. So your Ct is equal to 1 minus e to the power minus t by capital T, with C0 equal to 0 and C infinity is equal to 1. There are other aspects that are also be calculated. That is, what is the error response? How the error is changing. Now, what do you mean by error? We have ensured that the final value of the response reaches a steady state value, that is 1. What is your input signal? Unit step 1. So we shall consider how this particular output signal is following the input signal. That is called the servo system. That you will learn in the control system section. But this is how the error is calculated. So error is calculated as ET is RT minus CT. So if you calculate this, you'll get e to the power minus t by capital T. So what will be the steady state error? That is, at steady state, what will be the steady state error?
0.
Right, limit t tends to infinity, et, so it will be 0. As it follows from the response is, the steady state value is same as the input value. So the system will track the unit step input with 0 steady state error. Number 1. Next, the system response will be dominated by this time constant t. Okay. So the lesser the time constant, the faster will be the system response. How? এখানে আমি বলতে একটুখানি মিস করে গেছি, দেখো ওই জন্য বলবো বড় করে I'll draw it much more clearly. Suppose this is your steady state value that you are considering, or this is a unit step input. Say this is unit step input. Right? So we'll be discussing about the response. Now we have seen that slope at t equal to 0 is 1 by t. So if it continues to grow in this particular rate, when it will reach the steady state value? It will reach the steady state value since the slope is equal to 1 by t at t equal to 0 plus. So it will reach the steady state value in how long time? Right,
T.
in t. So this is how the actual definition of time constant came. Had the system been allowed to move in this rate, it would reach the steady state value in ideally t time. But that is not the case. The rate of change of output is being reduced because of this feedback effect. Okay, that's why it takes not t but something more than t. And if you just calculate the time it takes to reach this at time t, it only reaches 63.2% of the final steady state value. Then obviously, the less the value of t, the faster will be the system response. Okay, or it will reach the steady state value much faster. The time constant determines the speed of response of the system, right? So by reducing capital T, we can reduce the time taken to reach the steady state value, or you can increase the speed of response. So this is for step. So what about in unit ramp input, for which we have RT equal to say T. So your RS is equal to 1 by S square. So following that, what will be your CS? 1 by TS plus 1 into 1 by S square. Find out what will be the partial fraction. বল এটা কি হবে? আচ্ছা আমি লিখে দিচ্ছি, দেখবে। আসবে, হ্যাঁ। So you will get your CT as T, there's a ramp signal, minus capital T. So this is your response. The actual response will be something like, okay, let me first calculate. What will be the value of C0? Will be 0. But you cannot calculate C infinity because it will be infinity. So it will start from 0 that you have concluded. So it will move like this until it reaches this, and this will follow this straight line drawn in red with this distance being capital T. So it will follow the ramp signal, okay, but not with the accuracy that it was following the step signal, because in this case you will have a difference of capital T. How that can be proved? Find out the expression for error signal. What is the error signal? ET RT minus CT. So it will be দেখবে কি আসবে, capital T 1 minus, right? So what will be the steady state error? Take a limit, it is to infinity, so it will be capital T. So that is why it will reach the steady state value, but it will follow with the steady state error capital T. Right? So the system tracks the unit ramp input with the steady state error capital T, which is nothing but the time constant of the system. So to reduce the steady state error, what you have to do? You have to reduce the value of capital T. So by reducing the value of capital T, you can reduce the steady state error following a ramp input. And we've already seen by reducing the value of capital T, you can increase the speed of response of the system. So obviously it will be beneficial to have a system with the value of T as small as possible, right? But physically in some situations, this capital T is already defined by say R and C. So you cannot change it, but it will be suitable for you to design a circuit such that the time constant is as low as possible. বোঝা গেল এটা? প্যারাবোলিক এগুলো দরকার নেই, কেন দরকার নেই একটু পরেই বলছি। লাস্ট যেটা বাকি থেকে গেল সেটা হচ্ছে ইউনিট ইম্পালস রেসপন্স। ঠিক আছে, ইউনিট ইম্পালস রেসপন্স, obviously in this case your RS is equal to 1, because actually your CS will be 1 by TS plus 1, and your CT will be 1 by T into the minus T by capital T. So this is your expression for unit impulse response. Unit impulse response means there's a sudden change, but it doesn't sustain. It moves up very quickly. Say this is your value. One, 0. This is your impulse input. I will be drawing the input with yellow. So let us see. This is impulse. input impulse. Say, so what will be the response? The response will be the thing is that if you consider CT like this, the starting value will never be 1. Sorry. Because what is your C0? 1 by T. So it will start from the value, say this is your 1 by T. And finally, following this exponential curve, it reaches the steady state value or 0. And actually, it takes around 4T to reach the 0 value. Okay, so this is a unit impulse response. And this is sometimes analogous to a sudden change in input condition, but which doesn't change for long. It just changes and comes back to normal. Just like in wind gust. A sudden wind gust has come and got back to normal. Right? It's like a tight slap. Instead of giving you scolding for half an hour, if one gives you a tight slap, it will be like an impulse response. Right? So don't take it personally. So next thing will be some important property. What is that property? Regarding that response. Okay, so let us first jot down the different responses. For unit ramp input, what was the CT? CT was T minus capital T plus T into e to the power minus T by capital T. Next, unit step input. And last but not the least, right? Now, if I again jot down these inputs, what are these inputs? Unit step input means, sorry, ut equal to 1. Color code is not maintained. First I have written ramp. So RT is equal to T, then ut is equal to 1, and then finally we have this as delta T. So by following these 3 expressions for CT, can you comment on anything? Can you find any pattern?
e to the power minus t by t is common in all this.
No.
Exponential decrement.
No. See, let me just write down this expression, then it will help you. If you take a DDT of ramp signal, derivative of ramp signal, what you will get?
Step.
If you take DDT of step signal, what you will get?
Impulse.
Agreed? Now take first derivative of this ramp response. What you'll get? You'll get the step response.
Step response.
Right? You take a derivative of this impulse, the step response, following this principle. In the next, you follow the same principle, take a derivative of this, you'll get this impulse response. Right? See, for linear time invariant system, since the inputs are connected in this manner, the corresponding responses are also connected in the same manner. So if you know either step response or ramp response or impulse response, do you really need to know the other responses, or you can simply integrate or differentiate the step response to obtain ramp or impulse response, right? If you integrate the step response, you'll get the ramp response. If you differentiate the step response, you'll get the impulse response, right? So knowledge of any one response will be sufficient. Agreed? That's all. And if you know the expression for step response, you can differentiate it once to get the impulse response, or you can integrate it once to get the ramp response. That's all.
Yes, sir.
Okay, fine. But only thing is that if you just think about the result, the nature of the response, the transient response or the other response, they're depicted by this differential equations. Or this, not the differential equations, this linear equations, not linear, the exponential equations, right? So once the response of step input is known, so you can obviously comment on what would be the response with respect to ramp input or impulse input. So no additional information regarding the speed of response, because this capital T exponential minus T by capital T, this indicates the speed of response or how fast this exponential term decays. Okay, so that will determine the speed of response. So the speed of response will be same for step input, impulse input, or ramp input. So from transient point of view, if you know the speed of response of for a particular step input, there is no need to even calculate the speed of response for other point of view, for other responses, because the exponential terms which depicts the transient part, this speed of response is depicted by this transient part. This is fixed for all the three cases. So the speed of response, no additional information regarding the speed of response will be obtained by calculating the ramp or impulse response. So does that mean we should not at all move on to ramp or impulse response? No, you should move on to ramp and impulse response to calculate the steady state error or the steady state behavior of the system. See, for unit step input, you find out that there is no steady state error. But for the same system, given the ramp input, there is a steady state error of capital T. So this information is not given if you just look at this step response expression. Okay, the transient response or the speed of response is depicted. That is same for all three cases. But the only difference is that the steady state behavior, to create the steady state behavior, you need to calculate each and every response. Okay, this is why it is important to calculate RT and impulse response and the ramp response. So in next course of our study, we shall only concentrate on the step input or the unit step response. And most of the performance specification or the performance indices for a system are determined or presented or defined in respect of a unit step response, step input, right? So in the next class, we shall discuss about the step response of second order system with reference to step input for variable conditions like underdamped, overdamped, critically damped, undamped. Okay, so I recommend you just to go through a brush up whatever you have taught regarding the different responses. Okay, so that I can very easily breeze past that. Okay, so I'll stop here today. Any queries?
No, sir.
Okay, thank you. And just okay.
Okay.
And,